To be the wind for the tree. To be the sun for the leaves. To be a mineral for the roots. To be something meaningful rather than harmful. To be a bird or a pollinator, insect. This year I felt closer to the trees than ever because of the induced immobility or because I had time and space to spend with them. The work translates the trees readable for the viewer, creating the vocabulary for the physiological processes that happen inside them. The sap going up the crones, the humidity of the trunk, connected with the humidity of the air and soil, their vertical position in the three axes, and how the tree feels gravity and wind. The 12 spectra of light that allow to analyze the conditions of the leaves.
Did you ever want to hear a tree talk? Did you ever want to feel how the water goes up the trunk to the very crones of the tree? Did you ever want to know how the wind feels for the tree? This project is based on the idea of Internet of Trees, verbalizing the tree sensuality. To be the wind for the tree is a poetry generator that takes the data from the Tree Talker Plus sensor to analyze 7 parameters of the tree vivacity and well-being in order to create variables within the sentence. The concept of Internet of Trees aligns with the Nature 4.0. Nature 4.0 corresponds to the idea of the fourth industrial revolution, and again we are thinking of the green infrastructures as the systems that are able of self-management. And in order for this to happen, what we need is the real-time, precise data on the parameters of the trees based on their vigor, well-being, and the risk of failure. And all of this can be done with the help of sensors that are connected to the internet, and the Tree Talker sensor can be one of these devices.
It was back in 2013 when the European Commission published the European Green Infrastructure Strategy, enhancing Europe's natural capital, with the aim of encouraging the development of green infrastructures at all territorial levels, national, regional, and local, and also to guarantee their consideration in territorial planning. So the European strategy defines the green infrastructure as a strategically planned network of natural and semi-natural areas with other environmental features designed and managed to deliver a wide range of ecosystem services. It incorporates green spaces or blue if aquatic ecosystems are considered, and other physical features in terrestrial, including coastal and marine areas. On land, green infrastructure is present in rural and urban settings. And the social functions of green spaces relate to general habitability level of the cities. We would probably stick to this definition. So the green infrastructure can be described as a network of natural and semi-natural features within and between villages, towns, and cities, reaching out into the wider countryside. These features range in scale from individual street trees, green roofs, and private gardens through to parks, rivers, and woodlands, transport corridors, verges, and the large-scale wetlands, forests, and agricultural land. Beyond constructing a network of interconnected green spaces, which is fundamental requirement for conserving biodiversity, the green infrastructure provides a large number of environmental, social, and economic benefits deriving from multiple ecosystem functions and services provided by nature, such as water regulation, erosion control, water purification, or the prevention of climate change. In the urban context, the benefits provided by green infrastructures are especially important due to their contribution to the health and well-being of the public. The numerous benefits include improvements to air quality, tempering of the urban climate, consequent reduction of the urban heat island effect, and the reduction of atmospheric contamination. The multifunctional nature of green infrastructure is underpinned by the concept of ecosystem services. The research found that economic productivity, health, and well-being depend on range of services provided by ecosystems and their constituent parts, such as water, soil, nutrients, and organisms. So generally speaking, these services include supporting services, those necessary for all ecosystem services, such as soil formation and photosynthesis, the provisioning services, such as food, fiber, and fuel, the regulating services, including air quality and climate, the cultural services, such as recreational activities and well-being, aesthetic values, and sense of place. Russian scientists have analyzed the current general construction plans of Moscow, St. Petersburg, Novosibirsk, Yekaterinburg, Nizhny Novgorod, Kazan, Chelyabinsk, Omsk, Samara, Rostov-na-Donu, Ufa, Krasnoyarsk, Perm, Voronezh, and Volgograd. As a result of this analysis, there has been concluded that the whole range of ecoservice functions of the green infrastructures is neither included nor valued in any of the cities named. The most widely mentioned is the recreational function of the ecological carcass. The second thing to be mentioned is the aeration and the air cleansing. A less considerable function is the sound pollution filter and the buffer zone creation. The anti-erosion ecosystem services are only mentioned in 2 general construction plans in Ufa and Kazan, despite the fact that this function should be acquired and acknowledged by all the cities that are situated on the riverbanks and in the steppe zone.
Now, why is it important to analyze the data from the trees and how it can help creating the smart urban infrastructure and especially the green infrastructure, and why is the green infrastructure useful for the city, for the cities and the people who live in them? So let's understand this concept of green infrastructure. So the green infrastructure is kind of a green belt or the green ecosystem within the city. It doesn't only contain the trees, but the trees and shrubs and the grasses, they certainly all are part of the green infrastructure. It also contains the rivers and the air and light. So all these parameters are included in the notion of green infrastructure. There is this funny test on how to measure the greenness of infrastructure within a certain city. So you can imagine a little rabbit or a hedgehog traveling from, say, north of the city to the south of the city. So if this little rabbit or hedgehog can do this, then the condition of the green infrastructure is right. If it cannot, well, I guess then it is not. So the total area of St. Petersburg is 144 hectares, and the percentage of the green infrastructure is 24, which equals to 35,000 hectares. That wouldn't be too bad in case all these trees were proportionally spread in the city. However, the 60% of all of this 35, are concentrated in 5 districts of St. Petersburg. Certainly, Kurortny and Petrodvorets would be the most considerable parts, but the other ones would be Vyborgsky, Primorsky, and Krasnoselsky.
In summer 2019, the Department of Landscape Architecture of St. Petersburg State Forest Technical University became a co-implementer of the project Smart Technologies for Monitoring, Modeling and Assessment of Ecosystem Services of Green Infrastructure and Soils to support decision-making in the field of sustainable development of cities against the backdrop of global changes. This project is being developed at the People's Friendship University of Russia in Moscow by the scientific team managed by Professor Riccardo Valentini. The head organization of the project is the Laboratory of Smart Technologies for Sustainable Urban Development in the context of global change, and it's also situated in People's Friendship University. In 2019, the monitoring was carried out in Moscow and St. Petersburg. However, the project imagines the creation of an operational environmental monitoring system called Smart Urban Nature for cities in European Russia. And the priority cities will be Voronezh, Rostov-on-Don, and Apatity, and the system is planned to be implemented in this year and the following year. By early 2020s, More than 200 devices had been installed in Moscow, and 10 devices had been installed at test sites in St. Petersburg, at Forest Technical University, the Botanical Garden, and in the Summer Garden. So according to the data of monitoring of wood species conditions, 30% of the trees have approached the natural limit of life expectancy. Therefore, an important problem is preservation of old age trees and the increase of plantings to replenish the lost plantations.
The idea of Internet of Trees is connected with the smart infrastructures, and these smart infrastructures work on several levels. So they are embedded in the soil and in the tree trunks. They are flying in the air. The flying in the air are the drones that can on one hand monitor the wildfires. On the other hand, they can be used for seeding the trees actually at quite industrial level. Once we talk about sensors on the tree trunks or in the soil, they actually comprise this idea of Internet of Trees. They are made up of, the Internet of Trees is made up of these sensors. Another way of tracing deforestation is the light radar, and this analysis of light and other changes in the tree infrastructure can also be analyzed through the machine learning and the neural networks. Once the changes are observed and the possible next stage can be predicted. The change in social terms that can be brought by means of Nature 4.0, smart forests and the Internet of Trees can be seen in 5 stages, or with the use of 5 strategies that Jennifer Gabriz, the leader of the Citizen Science Lab, has formulated. So the first step being the observation through the remote sensors, the observation of trees and forests, wider the forests, I mean. The next stage would be automation and optimization, and here the work can be the work of attacking, of alleviating the anthropogenic state. The anthropogenic trace can be done at a certain industrial scale. The next stage would be datification, and we can see the green infrastructure, the parts of the green infrastructure, the parks, the city forests, as the places where the data is being produced as the agents communicating with other societies. So this would make this objects of as parts of green infrastructure the active social agents. And the next stage would be participation and inclusion of wider social groups in observing and ameliorating the green infrastructure. And there are apps and like i3 or the open street where citizens of a certain town can add information on the conditions of green infrastructure, and hopefully all this will add to transformations and smart urban nature in particular. And the tree talker device can be seen as one of the stages, one of the steps within this 5 stages. This year has brought relatively considerable change into the management of green infrastructures in Moscow. There has been decided that the tree talker sensor, and to be more precise, 217 tree talker sensors will be used officially at the level of state management of Moscow city green infrastructure, and the Smart Urban Lab will participate actively in this process. This has become possible as a result of the 2-year experiment at Aptekarsky Огород, Bolotnaya Square, and the Botanic Garden of Lomonosov University, where the sensors had been installed, and the data obtained from them proved to be useful for the green infrastructure management. So at this point, the sensors are not only in Тимирязевский парк, Аптекарский огород, and the Botanic Garden of the Lomonosov University, but they have also been installed in 2 venues in St. Petersburg, in the Summer Garden and in the Forest Academy.
The main character of the work, the main mediator, the main translator of the desires and sensualities and the needs of the tree is the tree talker sensor, the know-how of the Nature Smart Lab, and the production of the Nature 4.0 company. So this character exists in 4 modifications: TT+, TT1, TT carbon, and TT fire. TT+ works with the defining the speed of the sap flow. The TT1 works with the speed of the worm's impulse. The TT carbon is focused on the carbon dioxide reworking into the sugars, and it will only be produced in January 2021. And TT fire is aimed at prevention and finding the forest fires. So the most important with this technology for comprehensive monitoring of the state of green spaces is the solution of 2 problems: assessment of vertical stability and the physiological state of green spaces. Within the framework of the project, Smart Technologies for Monitoring, Modeling and Evaluating Ecosystem Services of Green Infrastructure and Soil to support decision-making in the field of sustainable urban development against the backdrop of global change. The technology of continuous monitoring and data transmission using the know-how of measuring equipment tree talker is being tested in 2 modifications: TTG which determines the vertical resistance, and TT+, which assesses the physiological state of woody plants. The multifunctional tree talker device at the individual tree level provides continuous measurement, storage, and remote transmission of data on its vertical stability, angular deviation of the trunk from the normal along the 3 coordinate axes, water transport intensity, radial growth, photosynthetic activity, and the microclimatic indicators, temperature, relative humidity. The measurement of the above parameters is carried out on the basis of highly accurate methodological approaches. So the vertical stability of the tree is estimated using an automatic accelerometer, gyroscopic sensor. The intensity of water transport, a thermal dispersion sensor, temperature dissipation probe. Radial growth is an infrared distance sensor. Photosynthetic activity analysis of multispectral data, 12 spectra, visible and near-infrared wavelengths, about the sunlight passing through the tree crown. Measurements are taken every hour and a half, but this can be adjusted. The received data from the tree talker measuring device is regularly transmitted to the TT Cloud microcontroller, which in turn sends them to the web server using GSM network via GPRS modem. The tree talker device allows you to monitor in real time the dynamics of the physiological state of the tree, its vertical stability, as well as the microclimatic indicators of the environment. The tree talker consists of the microcontroller with the ATM Mega 328 processor chip enclosed in the case, acquiring signals from number of sensors designed for measurement of variables including water transport in xylem of the trunk, the sap flow, wood temperature and humidity, multispectral signature of light transmitted through the canopy, tree trunk radial growth, accelerations along 3D coordinate system used to detect tree movements, air temperature and relative humidity, which can be additionally completed by soil temperature and volumetric water content. A TT is typically mounted on the trees by means of a belt tightened around the tree trunk and powered by a combination of high-efficiency lithium-ion batteries and a small solar panel attached on the battery case. Depending on enabled measurement types, acquisition frequency, and installation locations, the battery's autonomy is expected to span from 3 weeks to a year. The sap flow density is retrieved according to the heat balance method developed by Granier in 1985 by monitoring the temperature of two 20mm long probes inserted into the stem wood at 10 cm distance along the trunk vertical axis. The probe in higher position is heated, while the lower one provides the stem wood reference temperature and is additionally equipped with a capacitive sensor for wood moisture measurement. This needle is very thin, so it prevents the creation of the wound and thus the infection of the tree. Similar technology is used in a dedicated probe for the volumetric water content. and temperature measurements. Multispectral measurements of sunlight are performed across 12 bands, covering the visible and near visible infrared spectra, and centered at wavelengths of 450, 500, 550, 570, 600, 610, 650, 680, 730, 760, and 810 and 860 nm by means of spectrometer with a field of view of 40 degrees mounted on top of the TT case. The stem radial growth is measured by an infrared pulsed distance sensor positioned at a few centimeters from the tree trunk surface and kept in place by a carbon fiber stick anchored in the xylem. Any stem radial increment therefore translates into a reduction of the distance between the sensor and the targeted tree trunk surface, which according to laboratory tests can be determined with the resolution of not less than 100 for sensor target distance up to 5 centimeters. The TT incorporates an accelerometer, providing data on changes of the device position over time and instant accelerations of tree trunk where it is installed. This technology can be conveniently applied to monitor the root plate tilt, as well as the flexion and the accelerations that tree trunks receive under the force of wind for the evaluation of tree failure risk. The thermohydrometer embedded on the microcontroller completes the set of sensors. Exchange through the device case is allowed by 0.6 millimeter wide circular hole covered with water vapor permeable membrane. The tree talker features a wireless connection using powerful lower power chipset LoRa for data transmission to a node managed by another microcontroller TT Cloud, serving up to 48 devices in one cluster. We suggest 20 to avoid data collision and data transmission. St. Petersburg Forest Technical University has been founded on the 22nd of April 1827 by Nicholas I. To be more precise, the first Forest Institute was founded in 1811 at Tsarskoye Selo, and the territory of the contemporary park of the Forest Academy was the territory of the farm by an Englishman, Davidson, but it was confiscated by the state because he wasn't paying his debts, his credit debts. So after the territory was acquired, the institute was transported from the Tsarskoye Selo, and around the building of the institute, there has been a park. The park was comprising, by the moment of its formation, it was comprising 277 dесятins of soil, and there were trees there of different genera. However, there was also marshes and sands. So once the sands have been dried, the park was aimed to be certainly a recreational area of the vicinity, but was also aimed at giving the students an opportunity to have some practical classes in growing and breeding plants. So at this point, the territory of the Forest Academy is bordered by the Karbasheva street, Novorossiyskaya street, Novosilievsky lane, Большой Samsonevsky Avenue, and the two parts of the park are divided by the Institute Lane. The botanic garden of the Forest Academy is a specially protected area of the federal meaning, and the park, despite the botanical garden, or rather inside the botanical garden, there is this interesting space of the nursery planting garden, where the species of exotic and less exotic plants are being experimented on, and their decorational and economical properties are being studied. So it seems the botanical garden of the Forest Academy seems to be the most appropriate place for the tree talker sensors, and hence first in St. Petersburg they were installed here. The data that you see on this Excel table, very legible. I can imagine that you immediately understand how the tree feels. So hence, this is basically why we're doing this text generator, to slightly humanize this scientific data from the tree talker. But let me give you a little bit of guidance on what you see here. So here you see the two types of data. The data designated by number 45 and the data designated by number 49. Data designated by number 45 would be the data from the main tree talker sensors, including the accelerometer, the thermal probe that allows us to learn about the sap flow, the infrared annual circle measurement device, and the thermohydrometer that gives information about the temperature and humidity outside, as well as the humidity of xylem. Number 49 data is the data from the spectrometer that analyzes the tree canopy in 12 visual spectra. However, there are, I'd say, 2 points where you can see any information about the condition of the leaves. The green leaf would be the one visible in the spectrum from 700 to approximately 900 nanomicrons. The leaf, which is slightly yellow, slightly damaged, would be visible in between 400 and 600, and 700 and 800. There would be 2 peaks. And the leaf, which is completely yellow, would be visible in the gap between 400 and approximately 600 nanomicrons. So let's look at each line of the text. So the first line makes a general statement on the tree physiology. The second translates the data from the accelerometer and the position of the tree in X, Y, and Z axis. The third interprets the thermal probe and the speed of the sap inside the tree trunk. The force is derived from the spectral analysis data, and since the light is the only thing that actually changes very quickly during the day, this is probably the most dynamic type of data. And the fifth line comments on the tree radial growth. So that is the information that definitely doesn't change very often, since we talk about the annual growth rings.